will introduce myself, I guess. I am Edoardo and I am a faculty here. I'm also part of the crypto group, like Dr. Shimaev talked in the last installment. And so this is the second installment of the crypto seminar. And I work in code-based cryptography, so I'm going to introduce the field today if you have not seen it before, and if you want to know more about it, then you can also talk to me. So I'll try to give a survey today of what the field entails and then what are the things that we're working on. And as I said, if you're interested in this, please come and talk to me. Also, we have Paolo here. Still for this week is my visitor. He'll be my research visitor for a few months. And we're working together on some of these things too, so we can discuss all together if you guys want. Okay, and then feel free to interrupt me with questions, of course, at any time. So this is the outline of the talk. As I said, it's very basic. I'll just introduce the field, talk about code-based cryptography, and then present what the recent directions are, at least two of them. So the motivation for the work in code-based cryptography, first of all, I think I should introduce exactly what public key cryptography is. If you're new to the field, traditionally cryptography is the way of exchanging information securely, and the intuitive way is to just share a key and then just we can communicate securely, no one else can understand what we're saying, right? But public key cryptography does this in a much more sophisticated way, and I would say interesting too. So this was introduced by a bunch of guys towards the end of the 70s, Riva, Shamir, Edelman, most notably Diffie and Hellman. Right? And the key framework is not symmetric like the way we're used to think about cryptography, but it's rather asymmetric and it's based on a hard problem. So we have two keys instead of one, and then they're used for different things. Yes. So basically, if I want to communicate with another person, I'll take a plain text, which is a message I want to send, and encrypt it using the public key. The public key will be the public key of the user that I'm sending the message to. So this is public; everyone can see that. I can take this public key, communicate by encrypting the message, sending the message over. This becomes a ciphertext, and then the person I'm communicating with will receive the ciphertext and decrypt it using his own private key, which is associated to the public key. So this trapdoor here, which is this hard math problem, sits exactly in between public key and private key and allows to decrypt. Yes, so this is the trick part to invert this otherwise one-way function. Yes, and this is ideal for a variety of applications. For example, the most immediate one is I can communicate with someone without having to share a key. That was the idea at the base of it, right? So if I want to send a message to Brandon, I'll just look up Brandon's public key, encrypt my message using that. Everything is public, and then Brandon gets my message, and then he can decrypt it because he has the private key. No one else has the private key. And this is protected by the hardness of the math problem underlying my system. But of course, I can do much more, and this is why this public key cryptography is so interesting. I can do signatures, right? For example, I can authenticate a message rather than encrypting it by computing some private function on it. This is kind of like a decryption, if you want, because it uses the private key. And then I append the signature. The signature is like a traditional pen and paper signature. It's a piece of information that goes at the end of the message. Yes, and so then everyone can check that this signature is genuine by using the public key. Yes, I can also do key exchange. So without actually exchanging messages, what we can do is you and I agree on certain values, and then we exchange a shared symmetric key. So if I want to use symmetric encryption for a variety of reasons, I can still do that, but I can use public key encryption to solve the issue of exchanging the key. Yes, I can do much more group signatures, a whole lot of different applications. And so public key cryptography opened the way for the modern security and communications. Now, what's going to happen is that in a few years, large-scale quantum computers might be reality. Exactly how many years this is going to be, we're not sure, right? We can estimate 10, 15, 20. It depends on also what you mean by large scale, right? But then we already have Shor's algorithm, which is capable of solving some of these problems that we know are hard with traditional computers. For example, the RSA crypto system is based on the habits of factoring. And so Shor's algorithm will allow to factor, right? So you have a very, very large number. Suddenly we can factor this in polynomial time. This is not something that we can rely on in terms of security anymore. And similar for DSA, digital signatures based on this cryptologarithm problem. Again, can be solved by Shor's algorithm. And everything that is based on elliptic curves, which again uses like a variant of the discrete logarithm, which we instantiate on an elliptic curve. and the Diffie-Hellman key exchange. So a lot of these are behind our current communication. Yes, behind TLS, SSL, signatures, key exchanges. I mean, so once we have quantum computers out, these problems become polynomial time. We can't rely on the same crypto that we used to do since the 70s. And so finally, the community is starting to move in the direction of what we call post-quantum cryptography, and NIST, which is the National Institute for Standards and Technology, which is the institute that regulates all the federal standards, has launched a call for the standardization. So they mean to replace the standards for key exchange, signature, and encryption with new primitives. And so this was launched in 2016, and they received some candidates in 2017, and they're now going through the process of standardizing this. And there are traditionally 5 areas that are considered post-quantum. One is very recent, and it's based on isogenies. Shibai talked about lattice-based cryptography 2 weeks ago. And so this mostly is based on the hardness of finding short vectors in lattices, I would say, or closest vectors. Hash-based cryptography and multivariate cryptography are of a slightly different nature, so consist of, for example, solving multivariate system of equations over finite fields. Hash-based boils back to the hardness of breaking hash functions, if you want, which is not technically a math problem. Yeah? So this is somewhat more mechanical point of view, which is in a sense even better. And then code-based cryptography is the area that I work on, which is mostly boils down to the Michaelis and the writer crypto systems. Yeah, so this is one of the 5 principal areas of research in post-quantum cryptography, and I would say it's only second to lattice-based cryptography in terms of popularity, with certain differences that we're going to explore. Okay. So what is code-based cryptography? Well, it's based on linear codes. So traditionally it comes from Robert Michaelis, who introduced the field, and he proposed this crypto system based on linear code. So a linear code is simply a subspace of dimension k, or fq to the n. So it's a vector subspace. Yes, so imagine you have a bunch of vectors, and then this form a vector space, vector subspace. Yes, and then they're able to correct a certain number of errors occurring in code word. So what is a code word? It's a vector of fq to the n. Yes. And then we can identify whether certain code words contain mistakes by means of a decoding algorithm. Yes. Exactly how this is accomplished depends on the specific code that we are considering. For example, we can check the parity of number of bits in the code word, or several other properties which depend essentially on which space we're choosing. Yes. So what I do is traditionally I choose how do I define a vector space. I choose a basis for it. Yes, I choose k vectors to form a basis, and they generate all the other vectors. These are all the code words of my code. And so, as I said, you can get certain properties of this by looking at how these code words are formed, what is the distance between them, and so on. And so we measure these things we call having weight, which is the number of non-zero positions, right? So the weight of a word is how many non-zeros you have. And then the basis that we use to form the space, we put in a matrix. Just because it's convenient, we put it as row over matrix, and then this forms what we call the generator matrix. So, because the code is linear, I can take linear combination of these vectors and make it into more code words, right? So I can, and this corresponds to summing certain combinations of the rows of G. This is what we call this generator matrix. And so each code word comes from a certain mu times G, where mu is like a combination. We can even put this in systematic form, which means that we have the identity matrix on the left, where we can see exactly the first 3 symbols, which is symbols of mu. Yes, this is traditionally what is used to encode. We also have another way of defining what belongs in a code and what doesn't. If we take the parity check matrix in this matrix H, we define code words as the vectors that make the product equal to 0. This product is called syndrome. So if we do H times X, and we get 0, then we know this is a code word. If this is not 0, then it's not a code word. So for example, if we were expecting a code word, we can tell, okay, some error occurred here. Right? And again, we have a systematic form for H, which relies on the one that comes from the generator matrix. They are highly connected. In fact, there's a lot more theory behind it, of course, because this also defines a code that is the dual of the other one. So we have 2 different tools to define a code, but the same code can be defined by 2 different matrices. Yes. Okay, how do we use these things to make cryptography? As I said, the first idea comes from Michaelis in 1978. So if you look at this, this is the same age as RSA and Diffie-Hellman. It was already proposed back then, and in my limited experience, I can tell you probably it was discarded simply because it had some problems, they are now less relevant than before, but we'll talk about it in a second. So the hardness, the mathematical problem behind is that of decoding a random linear code. So if I don't know anything about the code that I'm using, if I just take a bunch of vectors, independent vectors, and make them as a row, this is a random code, then I don't know anything about its property, right? So then when I try to decode, say I get a code word in which some bits are flipped and I have some errors, then I don't know anything about the properties of the code. The only thing I can try to do essentially is to brute force and then see if I can get, imagine that I can try flip some bits and then see if I get syndrome 0, for example, right? It's something similar to that. So this is good because it's very hard, it's an exponential time attack. Right? So how do we implement this as a crypto system? We choose an error correcting code from a certain family that I know how it works. For example, binary Goppa codes was the proposal of Michaelis. Right? So if I know that this code is a binary Goppa code, then I have a bunch of guarantees like, oh, the minimum distance between every word is this much. Right? And then the generator matrix has this form, and so on. So I take something that I know how to decode. Right? So with binary Goppa codes, I can decode up to, say, T errors. Yes? Because there is a particular relationship between the code words. And then I have to hide it. Of course, this is the tractor. So I scan it. So say I have a generator matrix G, which defines a Goppa code, which allows me to decode. I hide it by multiplying by S and P on the left and on the right. Now, S is traditional and invertible matrix, so this corresponds to a change of basis. It does not change my code. It just creates a new basis. And then P is a permutation matrix, so it moves my column around, it permutes my columns. So again, I go into an equivalent code, but the result is that SGP is something that I no longer know how to decode. Yes? So I get code word in an equivalent code, but I don't know how to decode this one. So I've gone from a code that I know, I'm going to keep private for me, to a code that looks random. Okay? And then I can encrypt by intentionally putting some mistakes. Right? So I put my message, my plaintext say that I want to send to Brandon, I'll put it in a code word, and then I flip some bits intentionally because I know how to decode this thing, but no one else does. Yeah, so everyone sees SGP, it knows it's a word in this code, but this code they don't know anything about. So the scheme is probabilistic also because it means that every time I encrypt, I may choose a different set of bits that I flip. Yes, so it's not necessarily the same ciphertext that I get out of the same plaintext. And then the decryption uses the private key, which is essentially the input to the decoding algorithm. Yeah, so I get this noisy code word, I know what the structure of the code is, so I can decode, but everyone else will just see a noisy code word, and they don't know how to decode it. So it's very simple, the description, right? I could say in one sentence, right, it encrypts by embedding the plaintext in a noisy code word. And the encryption algorithm is very fast because it just consists of encoding, which is vector times matrix, and then you add some error position, so you flip some bits. So it's a very simple encryption algorithm. The decryption requires a decoding operation, which is a little bit more involved, but still the arithmetic is very easy. Yes, we're just using vectors and matrices, and it's all binary. So this is an advantage, for example, of code-based cryptography compared to other types of primitives which use more intense operations over rings or larger fields, and then complicated distributions and so on. And most importantly, of course, we are all doing this because there's no vulnerabilities against quantum computers. All we know is that the search, when we look for information sets, when we try to sort of brute force the coding, more or less refined, this search time is kind of halved if I use a quantum computer, because there is a standard algorithm which is due to Grover, which is used to speed up search algorithms. So I get sort of like a half of the security exponent, but this is not dramatic. I just have to account for it when I choose parameters. Okay, so what's the drawback is that I get really large keys. And this is what I was saying at the beginning, is probably the reason why Michaelis was immediately seeing as well, this is an interesting crypto system, but it's so big, I'm just never going to use it, right? So if you look at original parameters from Michaelis, code length was about 1,000, and code dimension, so the amount of vectors in the basis, so this is the dimension of the code, the rows of the generator matrix is about half, so 500. So 500 times 1,000, even if you're talking about bits, it's a lot of bits. It's in fact 67,000 bytes, yeah, which is 67 kilobytes. So you get a key of 67 kilobytes, that's really bad, especially in the late 70s. Yes. First, RSA uses, say, a large number to factor. This is in the order of 2048 bits. Yes, 2 kilobytes. Say. So there's an obvious discrepancy here, and let's say in the 70s this was deal breaker. Yeah, so you have a huge key. Nowadays, even Michaelis parameters are they're kind of old. Right? So they provide not so much security, but they give you to enlarge it, so you get keys that are on the order of, like, say, maybe a megabyte. Yeah, so really, really big. So this is traditionally being the drawback. Okay, here's the one picture description of McEliece in sort of like a modern fashion. We choose an error correcting code. We choose a code description for it. This could be any code family. It doesn't have to be binary GOPA codes. It could be some other class of codes. Maybe some of you have seen some code in theory. You know, there's several different types of code families. And we keep this private code description that allows to the code, and then we public some sort of scramble form. In fact, systematic form normally suffices. Yes, this corresponds to a scrambling. And then to encrypt this is very simple. We take the message, we put it into a word, and then we select a random error vector and we create the noisy code. This new equals E. And then the encryption just simply applies the decoding algorithm to it. You may have to unscramble something, multiply by inverse metrics or something to prepare for the decoding, but essentially it's just that. There's also a dual version which is proposed by Internet. This is completely equivalent. We've said before that we have generator metrics and parity check metrics, right? So rather than encrypting as a noisy code word using the generator metrics, we could encrypt using the parity check metrics. And then our hardness becomes the syndrome decoding problem, which was proved to be NP complete. So we have a clear advantage there. This was improved by incomplete in the late 70s. The problem is the following. If I have H, which is certain metrics, and a vector Y, of lifetime minus k, and I fix the target weight, say omega, find a word of this weight or less, like a low weight word, such that h times e transpose is equal to y. This corresponds to finding the error vector e, essentially. So it's an equivalent version to the decoding problem. Right? The decoding problem is given a noisy code word, recover the error. This is the same thing. Yeah? So if I take the noisy code word, for example, I can multiply by the syndrome, and then I get exactly SDP. And it's possible to conduce one problem to the other, like you do in complexity theory. So this is an NP-complete problem. The decoding problem is also. Yes. And so this guarantees that there is a unique solution if the weight is below the threshold in the code GB bound. And it's easy to show that this problem is equivalent to decoding, exactly like we were mentioning before. Okay, so this system is equivalent to McEliece because it's based on this instance rather than on the noisy code word. So what I will do. And of course, there's one difference we'll see in a second, is that the system is deterministic now. And so what we do is same key generation, except that I publish H instead of G. And we've seen that H and G are related. Yeah, so once I have H, I have also G. In fact, the systematic form is about the same. And then to encrypt, instead of taking a code word and adding some errors, I just put my message in the error vector. Yes, how do I do this exactly? It depends again on the particular application and implementation, right? But I take my messages at 100 bits and I put it into the error vector. Yeah, so normally this requires converting your message to a fixed weight string. It's a little bit cumbersome, but this is converted to. And then to decode, I just take my syndrome and I just apply the decoding algorithm to this. Yes. In fact, the first step of most decoding algorithms is take the code word, noisy code word, compute its syndrome, and then start the decoding process. So it's really the same thing. Except that here there's no randomness because my message goes into the error vector. So this is completely equivalent in terms of security and description, and it's just a variant that normally is preferred because deterministic crypto systems have some advantages. Also, if you take H instead of K, you have different properties and so on. So it may be equivalent to choose this or McEliece's version. Okay, so here we come to the first challenge. Yes?
I have a question. Can you go back to, is there any specific distribution we are using to choose the correct encode C?
No, this is not. So you have, depending on your code family, you have some items that you have to choose. For example, if you're using a GOPA code, you have to choose a certain, say, irreducible polynomial and a bunch of support elements that are distinct from each other, blah, blah, blah. These are normally chosen just entirely and uniformly. Yes. So this is how you choose the code family. Other class of codes, for example, that we will see later involve choosing certain sparse metrics or whatever. Everything is done uniformly. Yes. We just pick one in the family. So for this reason, we want the family to be large enough, and also so that it's not recognizable the key. Any other question? Okay, so key size is clearly the first challenge because we get these large keys because we have to publish these oblique metrics. And so with this next submission that is called custom McEliece, one of the semi-finalists if you want, We preserve the original McAleese approach of taking binary GOPA codes, and then we do nothing else, essentially, and we get keys that are about 1 megabyte. Now this is a huge problem in certain applications. For example, if you're trying to fit this onto like an embedded device or certain other situations. And so what we can do is either we change codes, right? Maybe we have some code that has like smaller matrix or something, and this didn't prove to work very well, or we can try to describe this big matrix in a compact way. Yeah? So imagine that I have a way, for example, to describe the whole matrix just in terms of the first row or the first few rows. Right? This would be a and so this is the idea that was initiated by Gaborini in 2005 and then was further explored. For example, what is a quasi-cyclic code? It's a code composed of circular blocks. So each matrix, each block is a square block which is circular. Yeah? So each row is the shift of the previous one. And this corresponds to a certain property of the code in which each code word you can shift by one position or any number of positions and it's still a code word. Yeah? So in a cyclic code, you can shift all code words and still get code words. In a quasi-cyclic code, you shift block by block. Right, but we still have this property about your code words, and so the matrix reflects that. Yes, so now we get a matrix that looks like this or like this, depends on your parameters, dimensions. And so you see in each block I only need to give the first row, right? And if I choose my scrambling compatibly with this, so my permutation is block by block also, my invertible matrix is also circulant and everything is preserved, and then my public matrix is still circulant, or quasi or block circulant, right? And then I can describe it very compactly. Yes? And this is an advantage because now essentially I go from a sort of like n squared to an n sort of dimension. Yes. So instead of publishing say 500 by 1000, I publish only the 1000 bits. Now suddenly this makes these crypto systems competitive. I also have other ways of transforming the codes. There's a whole literature about this. For example, dyadic codes. These are dyadic matrices. You see there is this nice picture with the colors. And you see it's like an A, B, B, A. Right? And then each A and B are themselves dyadic, so it's a recursive structure. It also corresponds, if you want, to a bunch of permutations in the first row. Yes, each row is a permutation of the first one, just in a different way. Is this dyadic permutation? So we can find families of codes that verify this on that property, right? Obviously, one starts from GOPA because this was what traditionally was used, but the Kyrell and et al. Work here use the generalized Solomon codes with quasi-cyclic structure, so GRS. I also presented a work on generalized Srivastava codes, which is, if you want, a generalization of GOPA codes using the quasi-dyadic family. So you can kind of mix and match, and essentially if you put conditions on, say, a generator polynomial or this and that characteristic of the code, you can get a code that satisfies this algebraic property. Yes, this is great, so then you can publish a public matrix. This is compact, you solve the problem. Except, remember, we have very mean attackers in cryptography, and they have a lot of power already. So if you give them even extra information now, they can try a brute force, right? They can say, set up some variables and try to get your key, but if the key space is very big, then they have a lot to solve, yes? But if they know that the key space is, say, circulant, then they can set up the system of equation and knock off a lot of variables and equations, and then suddenly this becomes solvable. So this became a critical algebraic attack initiated by Frege, which we know now as Sept. And it kind of breaks everything in terms of circulant and dyadic matrices when we use them with these kind of codes here. Okay? So we have to go very big in dimension, then we start losing the advantage that we get. Yes? And so after a few years of fixes, and then a new attack, and then another fix, and then an attack on the fix, and then the keys are getting bigger and bigger, and then we are less confident that this approach works. So what's the problem here is that codes, algebraic codes like GOPA or generalized Solomon, they're already characterized by having certain algebraic limitations. Yeah, for example, GOPA codes is the code words that satisfy a certain condition on evaluating the polynomial at the support points. So you already have some sort of variables set up in place for you there, and then you can knock them off even further by using these properties here. So then these codes are too structured to be secured. Then you have to take very large extension fields or get some workarounds and make your keys bigger, 100 kilobytes or something like that. Then, McAleese is 1 megabyte, this is 100 kilobytes. The advantage is not so clear. If you can have 10 kilobytes, great, right? But 100, not sure. It's worth it. Yes? And this is really what happened with NIST. Yes, either we had two submissions at NIST. One was mine based on GS codes with quasi-dyadic, and it had very small keys, but it was a little bit wobbly. It was attacked, and then we fixed it. And then they were like, what if you can attack it again? And then the key got a little bit bigger, and so we were not sure, or NIST was not sure about the security of this. And there was another approach based on quasi-cyclic code, where they stayed very high in terms of parameters, but then the keys were like, okay, 1/3 of my release, well, that doesn't really make much interest. Okay, so it looks difficult to provide security and a competitive scheme by using the traditional codes with structure. What we can do is use codes that have no structures to begin with, like these low and moderate density parity check codes. And the only characteristic these codes have is that they're characterized by a very sparse parity check matrix. Okay, so there's no algebra in there. The only algebra you have is that all the weight of your generator matrix, or sorry, parity check matrix, have constant weight. Right? So this is O1, so it could be like weight 10 or 20, whatever. Yes. And to decode this, we don't use an algebraic decoder because, again, we don't have any relation between decoders. We use a probabilistic decoder, which is this iterative decoder initiated by Gallagher in '63, which we call bit flipping. Yeah, so it's sort of like a majority voting thing. You just take all your parity check equations and you look like which ones are the more likely to carry the mistake. You flip those, and then you recompute, and then you keep flipping, and you see, and then eventually you get to the correct code word. Yes. There is a small possibility that at some point you make a bad decision, and this will eventually lead to a decoding failure. And so this algorithm is not ever correct, like the algebraic decoders. There is a very small probability, say 1 in a million, right, that the algorithm fails. But what's the advantage of this is that to distinguish the public matrix from a random one, essentially you're looking for low-weight corpus in the dual. Yes, because the parity check matrix is this matrix with like very sparse rows. And right, so what you're looking for, this is kind of like pure decoding. You're looking for these very low-weight rows. So really distinguishing the matrix from distinguishing the public matrix from the private one is no longer a big algebraic matrix scrambled to look like random. It's a sparse matrix scrambled to look dense. Okay, it's an entirely different problem. And so because this is the problem, then it makes sense to actually relax the notion. So LDPC codes were used traditionally in communication theory for their very high communication capability, right? Because it's so sparse and it's very powerful. The algorithm is very powerful, they're very fast. In cryptography, we don't need all this power. We're kind of downgrading, so we're raising the weight of the matrix a little bit more. So instead of being low weight, I decided to pull them moderate, right? And so instead of being fixed, say like 10, each row is like 10, well, they have something like square root of n. So maybe like 100 or 150 or something like this, depending on the typical length. Yes? And then this is still possible to correct with the same algorithm. It's obviously not as efficient, not as fast, but the trade-off is worth it because then when you look for this low weight, that is not so easy. Yes? So the distinguishing problem that depends on looking for low weight words is hindered. Yes? And so overall is a better choice than LDPC. And the nice thing is that now if we try to build structured codes with this class of codes, right, we don't have any structure to begin with. So what we do is our parity check matrix has to be sparse. That's the only requisite. So we take this sparse matrix starting from, say, a sparse vector, and then we just take all the cyclic shifts. This is obviously sparse because the cyclic shift is a permutation, so it doesn't change the weight of each row. And then we have a circulant block, which is sparse, and then there's no other requisite there. Right, so that's going to be my parity check matrix. I take 2 circulant blocks, right? Then I can make one identity if I want, right? And so the nice thing is I can describe all of this in terms of ring arithmetic. So you take the ring of polynomials, modulo x to the k minus 1, which is exactly the cyclic shifts. You know how polynomial multiplication works. And then really, this block is defined by the polynomial h0. This block is defined by the polynomial h1. I identify each polynomial with the vector of coefficients, right? And all the arithmetic works modulo x to the k minus 1. And we don't have the algebraic structure anymore. We have very small keys. We have a very fast decoder. Everything is very nice. Even the arithmetic is very nice because just to multiply a vector by matrix, I can use polynomial multiplication. Okay? So this is extremely promising. And when this paper came out in 2012, this was at the forefront of code-based cryptography. And the only problem is that it's still possible to somewhat exploit the sparsity and the decoding failures. Yes, so for more about this, we will have a talk by Paolo later on in the seminar series, and he'll talk to us about what is the problem with the sparsity here. What we are trying to do now, Paolo and I and our colleague Marco Baldi, is to describe a generic framework, which we call reproducible codes, for codes that we can describe in a compact way. So as we say, describe a code in this way, with, say, choose the first row and then do the cyclic shift, right? This is just like the easiest, stupidest thing we can do, right? It's just like we take the one word and then we just shift it. It's like the simplest permutation, the cyclic shift, on the simplest, like just the first row. Yes, but maybe we can do this in a more generalized way. So we can choose the first 2 rows or 3 rows or 10 rows or whatever, and then we can use another permutation, for example, the dyadic permutation or any random permutation I want, right? As long as this permutation is fixed, right? So instead of doing cyclic shifts, I can do like shifts the other way around or shift by 3 or whatever. Any permutation can come to your mind. In fact, it doesn't even have to be a permutation as long as it's a linear transformation. And if we're doing this with LDPC and DPC, we need to preserve the weight. So ideally, permutations are great because the weight remains exactly the same. But we could start with something, and then as long as the weight doesn't grow too much, it's still viable, right? So we can play a lot with this. And we hope to get still an efficient arithmetic, but lose some of the problems that it comes with the sparsity and the cyclicity. Yes, so this is what we're trying to put up now. And there's a lot to work on, of course, because well, it's a matter of looking at various permutations and various families of transformations, how they interact with the sparse codes, and how they reflect on the decoder, for example. Do they increase or decrease the decoding failure, right, and so on. So this is a promising avenue that we're working on now. And yeah, so we insist on this general framework for code in a compact description. So do you need to go? You can go. This is what we believe is the avenue for designing code-based crypto systems, encryption schemes, especially with key. Yes, so we still have the classic McAleese approach, if you want, the traditional McAleese approach based on binary GOPA codes. This works, it's secure, it's very well studied, it's been around for 40 years, it's great. It only has the one problem that the key is impossible to deal with, is 1 megabyte, so in a lot of situations we're just, it's too much, right? And then also the key generation, for example, is very slow. So the key is an issue, yeah? So it makes sense if you want to generate the key once and then use the same key that anyway you maybe store somewhere else or you store on like a large device or something, right? Then you use it many times. Then it makes sense. But if you have to say ephemerally exchange keys, like in TLS, where you have to generate a key repeatedly, this has to be fast and the key has to be small. Otherwise the crypto system is impractical. So then we believe that this approach is the one to pursue. And then once we nail down, we are in a good point now with the quasi-cyclic LDPC codes, but I think we can do even better. We also have other approaches. This will be the last idea about this, is we can use Rank metric. It's another metric for measuring codes. There are several metrics for measuring codes. Hemming metric, the one with the non-zeros, is just the more popular, but Lee metric or rank metric are alternatives. In rank metric, the weight is not given by the number of zeros, but is given by the dimensional vector subspace. So if you take a code over an extension field, and then each element is really like a string of elements of the base field, right? Then you can do this kind of projection that each element becomes a vector, and then you look at how many of these vectors are linearly independent. This is what we call rank metric. So each word, you have to imagine each code word is not a vector anymore, it's like a matrix. And the rank of the matrix is what gives you the weight. Yes. And the thing is, of course, this is a lot more complicated description. The attacks become harder. They are also at somewhat a more initial stage of study, and so we get smaller parameters. Yeah, so the complexity is quite big, so we can get really small codes. We use also random codes. We don't need to decode anymore with this approach. The protocol works substantially different, so I'm not going to mention it here. But there's another approach that we use, for example, in HQC and RQC. Yes. Okay, so here we come to the second challenge. So one thing that we know how to do fairly well is encryption. One thing that we don't know how to do is signature. So this is, if you want a bigger challenge, this is really where codes lose compared to other things like lattices, where we have very good and very efficient signature schemes. So signatures are important for sure. We use them in a lot of applications. And we have had several code-based proposals. Most importantly, CFS, I would say, also the Stern proposal, and none actually work. Yeah, so they're either impractical, right? You get large keys, or large signatures, or very slow signature times, or a combination of these, or also it's just plain insecure. Okay, so we're still kind of like a beginning stage for signatures. So what's the intuitive approach? I try to undo what the encryption does. Yes, this is what RSA signatures, for example, look like, right? RSA is like X to the E, and then you do that to the power of D. Yes, if you signature, you do like that to the D and then to the E, right? You just kind of, to sign you decrypt and then to verify you encrypt. So, yes. So for this, what we need to do is to sign, I decode. Yes, the decoding is what comes out of my tractor. So I can use what is called this hash and sign framework, right? Like in the RSA. So I take my message, I hash it, right? I don't want to sign my message, I sign maybe a hash of it. Yes. And then I try to decode this one. I'm the only one that knows how to decode, right? Like the writer Michaelis. So if I can decode this, then the verification simply becomes, oh, check that the syndrome is correct. Yes? So given a message M and a one-way function F and my hash function H, I compute the signature as inverse F of the hash of M. In this case, F is the decoding, right? So I will decode the hash of M, get the error vector, and then to verify, I just compute that. Yes, verify is F of sigma is equal to the hash. That's the literal done. So for code-based, the trapper is decoding, and this in paper this is great, right? But the problem is that decoding a random word is not always possible, right? So if I take a message that I want to sign and I hash it, this intentionally brings me to a random word. Yes? So I take a random vector, and then I try to decode this. Well, I don't know that this is a syndrome of some sort of low-weight error vector. So if this fails, then I have to do it again. And that's the only thing I can do. It doesn't seem very clever, but the only thing I can try is to try again. So what, I choose a different hash. I can add a counter, right? So I try hashing M1, and then M2, and M3, and M4, until I get something that is decodable. Now, if you know a little bit about coding theory, you know that these code words are quite sparse in the space. Usually each one is like surrounded by a little ball around them of decodable syndromes, but there's a lot of gaps. So I have to try many, many times. Yes. So with classical Michaelis parameters, I have to try like a ridiculous number of times to decode. Of course, this is not special choice. I just say, if I took classical Michaelis parameters and I take a random word in the space, this is the number of attempts before I find the decodable word. So of course I can choose my code a little bit more personalized. For example, I can choose it very rectangular. You see length to the 16 and then dimension to the 16 minus 144. It's basically like a very long thin rectangle. And then only 9 decodable errors. So it's like a very bad code, right? But it may be a little bit easier to find decodable syndromes and still about 9 factorial of them. Yes, so I have to try many times. What does this mean is that my signing time is ridiculously slow. Yeah, so it's like in the order of say 2 milliseconds, 3 milliseconds, so it is 1 order of magnitude away from what the current signature schemes do. Yes. There's also security concerns when you go to codes that are substantially away from the rate 1/2. So in coding theory, since your main problem is information decoding, is finding low-weight words. This one, when information decoding acts on a code of rate about 1/2, so the dimension is about 1/2 of the length, this is the hardest instance, yes? But if you are like substantially away, this becomes not so hard anymore, and it's also possible to distinguish the metrics, public metrics from the private one more efficiently. So this is really not a very good approach. And it's also still the problem of the large key. So I've done nothing, right, to solve that problem of the large key. So I have a scheme with a very large key and very slow signing time. Of course, there are some good things, right? For example, the signature is very short, it's just this low-weight word. Right? Once I decode, I get the low-weight word, this is very short, and the verification is immediate. I just do H times Z, and I check that this is my hash. Great, but it's not enough to fix this. Yeah, so verification is very fast, and the signature is very short, but this is not enough to fix the problem. And it doesn't really seem to be too much to play with this. So what the alternative approach is, the other one I was mentioning, initiated by Stern, is to not decode and play on the hardness of decoding instead, and use what we call feature-level technique. This is what lattices do, for example. So we take an identification scheme and we transform it into a signature scheme. Identification scheme works in this way, traditionally. So we call a 3-passed zero-knowledge identification scheme. I want to prove to you that I know some secret, right? So I will commit some random data, right, as f of y. You then send me a challenge C. I then do some transformation with my secret S, the challenge that you sent me, and the value that I committed. This is important, right? Because otherwise I could cheat. So I have to commit something ahead of time. And then I involve all of this in some sort of transformation, and I produce my response, and then you should verify that my response satisfies the commitment and the challenge and the public key that I had before. Yes? So the verifier accepts or rejects using the public data and the public key. So he will use the commitment, the public commitment, the public key, and everything public. And then Fiat Shamir does nothing else but playing this thing with yourself. So you commit some data, you then generate C as a hash of the message and the commitment. Instead of receiving it from this other party, you just generate it yourself. But this is like receiving because it's random. It's going to be a random hash. And then you send the response. And then all of this is your signature. And you send the signature, and then the verifier verifies exactly as if it was verifying the identification scheme, essentially. Yes. So this is what you do. Yes. Okay. So what's good about this? We can base it on SDP, and we don't need to worry about the coding anymore. Yes. But what Stern was doing was not the traditional 3-pass. He was using 3 commitments instead of 1, right? And then you could send some permutation of the word or some combination of permutations or things. And so the response depends on what challenge you're sending. And then I don't want to go into too much detail here, but essentially the impersonator can cheat in 2 out of 3 things. So he can fix some values ahead of time and hope that he gets, say, challenge 0 or 1. And he succeeds in 2 out of 3, and then if he gets challenge 2, then too bad. Okay? So this is bad because it means that even if you pass, even if your signature is accepted, it could be a cheating adversary. So you have to repeat the protocol another time, in fact, many times. Right? So if your challenges depend, so if your commitments and responses depend on your challenges, as I said, you can fix 2 of them, and then in 1 of them, the verification won't work. You will take your chances, right? But then you cannot accept anyone cheating, so you have to repeat. And so this is what you do. You're successful in 2 out of 3 cases, so you repeat many times. For example, if you repeat 35 times, then the cheating probability is 2 to the minus 20. Because essentially, for an impersonator to cheat, you have to always guess ahead the correct thing. And to do that 35 times, you need to be quite lucky. So this is still kind of like not so high level of security, but this already means a lot of communication, right? Because your signature has to include all these rounds of authentication. So this is not good. The signature becomes something like 150 kilobytes, and this is clearly not acceptable, right? And this is not even like the highest security level. So there are variants that reduce this communication cost. There is a variant that reduces the cheating probability to 1/2. But there's still like a flaw in the fact that there's a cheating probability, right? And then you have to repeat the protocol many times. So what you would like to do is a one-shot protocol where you send me a commitment, I send you a commitment, you send me the challenge, and I send my response. That's it, no cheating. So how do we do this? Okay, say I have a secret S, and the public key is hash of S for a collision-resistant hash function, and then I commit. And then my reply is CS plus Y, and then I can verify by calculating the hash function on Z and checking that this is equal to C, capital S by capital Y, which are all public values. And then use Fiat Shamir on this. This is great. Again, this is what lattices do. In lattices, we use vectors of small norm. For this lattice geometry, we include a norm. Right? So what this means is that they have a lot of positions that are non-zero, but of small magnitude. Yes. So this vector CS plus Y, it's all kind of small in that sense. You can kind of control the noise there. What we do for code-based setting, if we take our function to be the syndrome, calculation of the syndrome, and then H is your partition matrix for a random code, you don't need to be able to decode that. You just have to show that something is hard to decode. And then X is a vector of small norm. In this case, we don't have the Euclidean metric, we have the admin metric. Then we don't need to decode at all, but the metric is too weak. So when you see the vector CS plus Y, and we want everything to be low in terms of weight, then here I have a low weight vector Y, I have a low weight vector S, and a low weight vector C, and I hope that multiplying C and S doesn't grow the weight too much, and all of it has to be below a certain bound to make sure that your signature cannot be forged. And then we see this thing is all sparse. Then what we can do is just run a simple statistical analysis, right? We can see many signatures, and they all have the same S, where C and Y change. So eventually, the ones and the zeros in the response are biased, and you can really identify them. Okay, so this doesn't happen with the metric, but in the Hamming metric, I mean, the metric is essentially based on having very few ones and a lot of zeros. And so I am trying to hide my secret S by putting something sparse on top of it. This doesn't even cover all the positions, and it really doesn't work. And if we try to do more intense things, more complicated things, it's still vulnerable. And it's very hard to overcome these method limitations. It's very hard to prevent something like this to leak. Because in a signature scheme, you're allowed to see many signatures. The attackers are always allowed to see as many signatures as you want, right? As long as it's like polynomial number of them, I guess. And so you can always run some sort of statistical attacks, right? So you can try to do more involved things, but the metric is just not good enough because it's based on zeros and ones and sparsity, as opposed to the lattice metric. So there's some things that we can try to do about this, right? So before I mentioned the SDP is hard when the weight is low, which is the case of encryption. But also this is hard when the weight is very high. And this is something that traditionally was not done. And why is that not the case? Because if my error vector has a lot of weight, then I'm no longer guaranteed a unique solution. Yes? So in the case of encryption, this could give me a problem because then I don't get the right message back. But in the case of signature, this is not a problem anymore. So I just have to show that I'm able to produce such a pre-image if you want. So the solution is not unique anymore, but that's okay, because anyway, it's hard to find such a pre-image. I don't care that there's more than one, it's hard to find any of them. Okay? So we have this kind of situation where, say, up to the GB bound, it's hard. Then it becomes easy. So if you allow the weight to be, say, 1/2 of the word length, then this is just linear algebra. But then if you go very, very hard, very, very high in terms of weight, this is hard again. Okay? And so now we can use the CFH approach if we can guarantee that somehow remember with CFS we were trying to, I take my message, I hash it into a random word, and then this becomes like a random vector. I am looking this to be a syndrome of some sort of low weight word. Now I'm looking for this to be a syndrome of a high weight word. This is equally hard, so signing is again hard for whoever doesn't have the private key, but how can I be sure that I can get high weight word behind the syndrome? Because I don't even have a decoding algorithm anymore. Right, decoding works when my weight is low. So how can I do this? Well, you can use these codes which are called UU plus V, which is a particular class of codes which is just identified by exactly this name. You take 1/2 of the code which is the matrix U, and then the other half of the word is matrix U plus matrix V. So each word is like 2 pieces, a U piece and a U plus V piece. Yes? And then we can just decode using ISD, say in the branch version, one of the first ones, with some advantage, because if you have this UU plus V code, then you have a little bit discrepancy in what is hard and what is easy. In particular, in this part here of the weight, for anyone that doesn't know the UU, so you take a UU plus V code and then you scramble it. It looks random, so if you take a weight in here, it's hard, right? But because you have the UU plus V trapdoor, then you can decode that one, even if the weight is high. Okay, what you do is simply run information as a decoding with the instruction that you know. And so what you need to do is just to manufacture a high weight syndrome. You use rejection sampling, and then you can sort of, after a number of sample attempts, guarantee that your syndrome is high weight. This is what was called the SURF scheme, using binary codes. And the scheme was broken by the authors themselves, in a sense, before publication. So it came out, and then like, wait, there's a mistake, there's a vulnerability here, and then they withdrew the scheme. And then so the scheme is, if I use binary code, suddenly I can distinguish things. Again, there's some leakage. So then they came out again, and they did it on F3, so they used ternary codes. And instead of using the plain UU plus V codes, they use a generalized version of it. So there's always the trend in cryptography, right, to take something that is a little bit more generalized, maybe less obvious, right? So they take ternary vectors with 1 and -1, rather than binary, and then we take this generalized version of the UU plus V codes. There is still a little bit of concern about information leakage, but this should be fine. As of now, the situation is still kind of evolving. The paper is going to be published soon, so then we will see. There will need to be some time to evaluate this. Yeah, so there was first version of WAVE that was published, and it was containing certain imprecisions and things that were pointed out. And then second or third version of WAVE is about to come out and will be presented soon, and we'll see if this thing can work. There is a lot of skepticism right now about making signature with codes, so any advance in the area is definitely welcome there. So what are some conclusions? We have a very promising area code-based cryptography, which has many good features. Among the many good features, obviously, is the ease of arithmetic, right? So you can get very fast operations. This is great for encryption. You can get very fast encryption and decryption. There's at least two major research directions to investigate. The first one is reducing the public key. This is particularly relevant in encryption, because you may have to use the key more than once. You may have to generate it many times. And so we have this trend that started now on low-weight sparse matrix code. It needs to be perfected. There's still a lot of problems. And then the signature issue. Currently, there are no signature schemes at NIST. There were 4 proposed. I think 2 were withdrawn and 2 were broken or something similar. So there is just no approach that works. Even these recent approaches, like the surf scheme or the wave scheme, they still feature the big public key problem. Yes? Or big signatures or similar problems. So that's basically like a version of CFS. It solves the issue of finding the syndrome, but it doesn't solve the issue of the large key. And there are some concerns that I can see in using this with exactly codes, for example, for the reason that we saw before. So we're still a lot away from having an acceptable signature scheme based on codes if you can even find one. And there is a standardization project which is ongoing. We are currently in round 2. There will be a round 3 that has been announced, and there's many things required in terms of fine-tuning. So there's a lot of space for improving in terms of the theory, but also in terms of the implementation of these things. For example, finding a more efficient decoder, or one that guarantees less failures, or some more efficient arithmetic, or some other structure, or brick structure, or things like that. And there's definitely still room for new proposals and for breakthroughs. So if we can come up with a signature scheme, this would be a major result. Or if you want, if you can say distinguish copy codes efficiently from random codes, this is a problem that has been open for 40 years. That will be a huge breakthrough. But at any level, there's a lot of work to be done. And so if you want to know more about any of these things, get in touch. Keep attending the seminars. There will be more talks on code base. I can promise you this, and more work on this. Okay. And this is all. So thank you. Any questions? We can also talk about this later with more time, but if you have some short questions, it's fine.
Could you give a brief overview of the 5th area of research in post-quantum computing, or post-quantum cryptography, the
isogenies?
Yeah.
Yes. I'm not the best person for it. Maybe Brandon will be a better person. But so isogeny is an area of research that is based on elliptic curves. Now, traditionally, people were doing cryptography from elliptic curves based on the group of points and computing discrete logarithm on this group. Yes. So discrete logarithm means given, say, g and a power of g, find what the exponent is. Yes. In terms of elliptic curves, you can take a point on a curve, sum it with itself a bunch of times, so take a multiple of it, and then figure out what multiple this is. Yeah, so you can do discrete logarithm on the group of points of elliptic curves, and then you get the same instance of discrete logarithm. So you can do Diffie-Hellman and all these protocols here. The problem is that this is vulnerable to short algorithm. So then in isogeny-based crypto, what they do is take elliptic curves, but rather than looking at the group of points of a curve, they transform a curve into each other. So now the problem is given this curve and then another curve, so they can do a series of steps, so that you and I say we want to exchange a key. You take a curve, starting curve, I take another starting curve, we do a bunch of transformations which are exactly these isogenies, and then we get to the same curve in the end, as will be our shared value. And inverting these steps is hard, so finding what these isogenies are from the curves is the hard problem. Yeah, so for this, it's an entirely different part of math, of course. You deal with elliptic curves, valid fields. But yeah, it's a very new problem also, so it's being studied more and more. But yeah, it's a very interesting part. For a number of reasons, it's kind of different from all the other areas of post-quantum crypto. Yes. And I think there will be some isogeny talk, maybe the next one in the series or the one after that. Or you can talk to Brandon. Any other question? Also about the seminar series, or if you prefer different donuts or whatever. Okay, good.